All right, welcome in the live stream. You can already vote, and I think we're almost ready to go. Okay, I should probably, before we start, quickly say something about the video presentations. I've seen many groups have submitted something yesterday when I looked at it last night. I haven't looked at it this morning, so we'll do that later. You should see some feedback on Slido, on Canvas, I mean, whether your article was fine or not. There were only a few instances of articles that are published on ACM, on the ACM portal, the digital library, but were not actually from the journal, the specific publication, Communications of the ACM. And instead, they were from some conference proceedings. And the way I don't like those is they're for a very specialized audience. So I would very much discourage you from taking those, because they're just really tough to read without digging a lot into the background, whereas the ComACM article tend to be more and more approachable. And there should be some component of computer science. That's why I'm also a bit skeptical that, say, a Nature article is really suitable for this. I've been more lenient in the past, and it was to the disadvantage of the groups in almost all cases. So I'm trying to be more strict on this side and rather like protect you. I hope it's not too patronizing, but it's kind of a middle ground between, I know you're all interested in certain topics, but the assessment, on the other hand, has certain criteria, and it's just easier to match those from the articles from ComACM. So check Canvas and submit there if you haven't already, or wait, hold tight if you haven't submitted and I didn't get to answer it yet. We will have another continuous assessment coming up. If you carefully check my planned schedule, I wanted to publish it last week, but because everyone's busy with the videos, I don't think would have made much of a difference. So we'll discuss this on Thursday probably. There will be time till right before the Easter break, so at least a month. So it should be plenty of time either way. And you probably want to get the videos sorted first anyways. Let's have a brief look at the numbers behind these. So 37 people have voted. As always, hope we get a few more, but biggest blob is KMP, the Knuthmore spread algorithm, which got 16 votes. That's half of the people, almost. Closely followed by none with 8 people. And there's 7 variations of none, not sure, don't know, and stuff, etc. So it's one of these fun moments again where I'll bore a third to a half of the class to some degree, but the others will not have seen any of it and will be a bit challenged by the pace. So again, my compromise, I'll cover in this unit some material that you will have seen to some degree, maybe throw in a few extra bits, and the next unit will take this to parallel algorithms, and that's usually not something you've done. All right. Yeah, there's a few more votes, but the big picture seems a third to half of you have seen KMP. How about the others? Not much. So Rabin, Karp, and Boyer Moore you haven't seen. That's curious, because I tend to think of them as one unit. If you cover KMP, you often also cover the others. Well, I will do. So, welcome back to COMP526, and welcome to a new exciting unit, Unit 4, where we'll talk about string matching. And because string matching sounds very academic and not very useful, I put this subtitle here, because unless you're on Mac, and I don't know what the command is called there, pretty much throughout all programs, you can press Control F, and it gives you some ability to search. And that's really what we're doing here. We're explaining what's happening there, especially if this is a text editor or a browser where this is essentially text-based. And we'll come back later to the scenario that's closer to search engines or indices. So learning outcomes for this unit, I want you to be familiar with the theoretical notions and notations for strings. This is just something, again, I think computer science tend to communicate in these terms, so it's important to know those. And pretty much anything is a string, so they are ubiquitous in various ways in programming. But we'll take the mathematical notations into this game as well. I want to introduce three main algorithms, nicely abbreviated so that they don't make much sense if you don't know them, but that's Knuthmore spread, Boyer-Moore, and Rabin-Karp, all named by their inventors. And apart from just knowing how they work, I wanted to know what the differences in their performance are. It's a little bit like in sorting. None of them is completely dominating the others in all possible metrics. And instead, you'll have to sometimes mix and match a bit, depending on what you need. And lastly, it turns out that a component of KMP can be used for solving more sophisticated problems than just finding occurrences in a text. That's what string matching is, by the way. We'll come to the proper definition in a second. There's something more versatile going on, and so I want to teach you a little bit how this works, but nothing too crazy. I broke it up in nice little chunks, but some of them will be quite quick, in particular the first few. And we'll talk about another method that leads up to KMP first. That's string matching with finite automata. With that, let me start with the introduction, and in particular, all this notation around strings. I'll jump through some of these slides a bit quickly. They're both mostly for your reference. So first of all, what is a string? And we're not talking about underwear. It's a sequence of characters for us. And the characters can be something we'll talk about in a second. I want to first stress how ubiquitous they are. We use them for natural language texts in one form or another. All languages I know of are based on something like sequences. We use them for programs. They're used for websites and XML documents, which arguably websites should be, right? They're also in our body in a way, even though maybe encoded in a slightly more wet and yucky form, but DNA sequences that make up your genome are also strings in essence. And of course, bit strings, so when we get closer to computers, everything is ultimately somehow bits, and main memory is one, we think of it as one long sequence of bits. And so everything you do in a computer ultimately is a string if you want to look at it that way, because it's a sequence of bits. Although sometimes a bit more structure is imposed on these. What this also means, there's many different applications, also many different tasks and questions we want to ask about strings. So there's a lot of different things we can do with strings. And so this will keep us busy for a few more weeks. In this first unit, we'll look at finding in one long string, which we will call the text. We'll try to find a pattern. And the pattern is really just another string. So think of finding all occurrences of whatever, love in the works of Shakespeare. Might be one example. Another more esoteric one is finding a certain gene that's encoded in your DNA. You want to find if that gene is present in your DNA. That used to be science fiction, but it no longer is. You can ask a company to sequence your DNA, and they will get back to you with a 2 GB text file. And then you can do all these analyses if you can make sense of them. Yeah, virus scanners are usually based on something like finding specific patterns. They're often, at least the basic form is quite dumb. It's trying to find specific pieces in code that it knows are part of viruses. They can do more sophisticated things as well. Finding patterns like this is often a building block for other applications. For example, in bioinformatics, if you're talking about genomes, you often need slightly more sophisticated notions of finding strings. Usually things are not exact, but there's slight variations that are essentially irrelevant for how your body works. And now the promised notation. So bear with me for a second. Strings have an alphabet. We always, when we talk about strings, we always need to assume we know what are the possible characters that can occur. We assume that this is a fixed and finite set. So it's not like all positive integers. It has to be fixed. And so we can speak of little sigma, the size of big sigma, the size of the alphabet, the number of different characters. Now, if you think about English, you might think, okay, we have 26 letters, but then we have them in lowercase, capital, and uppercase, and we have all the punctuations and spaces, etc. So we probably have a few more characters to take care of. Traditionally, I think we'll talk about this in a second. So you know ASCII, this character encoding that has 128 characters that is usually enough for most Western European languages and English, for example, but already struggles with some like German because we have a few other characters that are not represented. So even there, you have not just the 26, but something like 100 characters. And this has recently been, or more or less recently been extended massively. So you now have Unicode with all the emoji, they all count as a separate character. So we have many, many more. I lost track. I think Unicode has around 150,000 characters. That's just something to bear in mind. So this sigma can be really small. It's 4 for DNA, 4 different nucleotide bases. But it can also be hundreds of thousands, depending on what the application is. All right, here are the nucleotides for DNA. Now, an alphabet tells you what a single letter is. A string is several letters. And we can write this as the Cartesian product of the alphabet. So it's just a string of 2 characters is a pair of 2 characters. Or in general, a string of length n is an n-tuple of characters. And that's the way to write that in mathematical notation. So you can write sigma to the n if you know the length is fixed. Then in this context, 2 other notations are often handy. The star means any length we don't know, including 0, so the empty string, which is this Greek epsilon. That's just the string of no characters of length 0. It's sometimes useful to be able to write that down without writing nothing. And sigma plus is, well, similar, but starts at 1. We will massively make use of the fact that a string is a sequence and we can access characters by index. And so we'll just write this like this. So other books or other lecture notes will vary the notation there. But I think it's convenient to not hide the relevant thing in the index, the subscript. So we use this array notation to access strings, and many programming languages represent strings as arrays of characters. So this is close to their implementation as well. And again, we started with 0, like all arrays in this class. So if a string has length n, it has indices 0 up to n minus 1. We'll just write 2 strings after each other for their concatenation, so just putting one string behind the other. And if you want to spell it out, you can use this multiplication symbol. And the last thing is this notation that we've used for sorting, for recursive calls of sorting algorithms already, so it's not really new. This is a slice of a string from positions I to j. So in this notation, including the endpoint, this notation will often be convenient as before for sorting. You know this already. So I is inclusive, j is exclusive. So any such thing is just called a substring of a string. Be careful. I will try to be consistent that a subsequence is something different. A subsequence is where I can take any positions as long as they're left to right, but I can leave out things in the middle. Whereas a substring is a contiguous subsequence where there's everything included from an endpoint, beginning point to an endpoint. Okay. And two more vocabularies is prefix and suffix. Prefix is something that a substring that starts at the beginning. Suffix is a substring that ends at the end. I think that's it. So time to wake you up, as always. Where do we have this? There. This can be a quick one. It's just testing if you paid attention. We need a few more votes. Even though it looks like a fairly clear result. Okay, 3, 2, 1. All right, we have a clear majority for true. That's correct. So remember, sigma star is a string of any length, including the empty strings, including length 0. Sigma plus is all strings of any length, but starting with length 1. So if you want to get sigma star from sigma plus, you just have to add the empty string again. Note that the empty string is kind of the only string where we don't have to obsess about its alphabet. It fits for anything because it has no characters anyways. All other strings should have a properly defined alphabet. The last part for this introduction and this massive list of notation is the formal definition of what the problem is like that we're looking at. So string matching. As I said before, the problem consists of two inputs. We have a text t, and now the text will always be of length n, or n will always be the length of the text. And p is the pattern that we're trying to find, which is some other string over the same alphabet. Note that they have the same sigma. And the pattern has length m. Now, we usually think of the pattern being relatively short and the text being relatively long. Formally, that's not part of the problem. It's just usually the case. Now, if the pattern is longer than the text, we don't have to search. But the pattern could be half the text, something. That's not unthinkable, but usually you can think of the pattern being small. And so for the output, it's a little, there's different variations. And I want to stress here that we find the first occurrence only for this point. So we try to find the smallest position, I, so that if I take the substring of t starting at position I find the pattern. And I take the smallest such I, so it's the leftmost occurrence, the first occurrence of this pattern in the string, in the text. If you want to find all occurrences, you can always find the first and then remove that occurrence from the string and then start the search again on the remainder. That's usually not a problem. There's another option. If the pattern does not occur at all, we return some special return value I'll just write return no match in the pseudocode. Different programming languages have different conventions, what's convenient there, so we'll keep it abstract. A variant of the problem, as I hinted at, is to find all occurrences. We'll talk about this at some point, because for some of the algorithms, you can find all occurrences in essentially slightly faster than searching for the first and then continuing from there. Because you kind of give up some information you learned already. But for now, we'll focus on always finding the first occurrence. Okay, let's do a small example. Here's a string. Where is he? If I say the pattern is he, I want to find where's the first occurrence. Don't be tricked. The first occurrence is here. There's a second occurrence, which is a bit more springs to the eye, but so the return value here would be 1. Remember, we start at 0. And if I search for who, I get no match because it doesn't occur. I wanted to stress that programming languages tend to implement this because it's a primitive. They don't always implement it in a very smart way. Maybe we'll come back to this. So in Java, there's a class string, and it has a find index. It has an index of method that finds in the first occurrence. And in Python, it's called find. Okay, and I'm confident that any other programming language you come up with will have an implementation of string matching too. Okay, one more practice round. It's not even strictly speaking about string matching, it's just practicing the notation again. I mean, pay close attention to the types of parentheses. Other than that, there's no tricks. It's just, I know, counting is hard, and then it's Monday. Okay. I see reasonable things coming in. Three, two, one, and locked. So I guess it's kind of clear, although some people sent no idea. So let's go through this very briefly again. If I had shown you this, it might have been a little more convenient. So here are the indices on top of the characters. And now you just start at the 3rd position, but counting with 0, and then up to 7, but excluding 7, so it's up to 6. So P526. Okay. Easy enough. Shall we do some real algorithms? In the next section, let's see our first actual algorithm for solving the string matching problem. And I call it the brute force method because it's essentially just trying all possible options. In a simple problem like this, this might be good enough indeed. But yeah, we'll see that it is not always that great. But it's a good way to start. It's also a good opportunity to think about the problem more generically. Well, what can you do to solve this string matching problem? And so I will assume that what we can do really at this, for all the unit except maybe for the last subsection, we can take 2 characters from the string or from the pattern, or from one from the text, one from the pattern, and compare them. Are they the same or not? That's pretty much what we can do. And so we call this a check if we do this between the text and the pattern. I think the notation is not so important. It will always be spelled out if I remember correctly. So we can check two characters, one in the text and one in the pattern. And we can try to confirm or exclude guesses, so positions in the text where the pattern might be found. So you can guess, maybe the pattern starts in the text at position I. So that would be a guess. And there's only so many possible guesses because the pattern can only start at every position. And of course, you can take a guess and then do a few checks, and they might either confirm that there is a match, or they might show a mismatch between some characters, and then you know this is not a correct guess. So a key feature is we need M checks for a correct guess, because we have to check all the positions. But we may be much faster with excluding a guess, because one mismatch is enough. If we know where to compare to find that mismatch, we can be much quicker. What we'll count in terms of the costs, remember, ultimately it's word RAM, but we want to make our life a little more convenient, so we'll count something more abstract than word RAM instructions. So here I'll usually count the number of character comparisons with the number of checks. We'll later allow some pre-processing, so we'll also compare characters in the pattern with each other, which strictly speaking is not a check according to that definition. But I will still want to count them as character comparisons. So this equality is fine for the first section, but maybe it should be taken with a grain of salt for later. But an immediate observation from this one is the number of checks can only be at most n times m, because then we have for every guess done all the checks. After at most n times m comparisons, we have compared all possible combinations of text and pattern positions. So if we haven't figured it out till then, we will never figure it out. And so guess what the brute force method does? It tries all the guesses and does all the checks. So you iterate with I through the positions where the pattern could start, and J iterates through the positions of the pattern, and you compare the appropriate characters in the text and the pattern. Now, if you ever find a mismatch, you don't really have to continue that loop. So the brute force method is already not completely dumb. It breaks out of the inner loop if it finds the first mismatch, and then returns no match. Well, it skips out of this inner loop and then goes with the next I. And if it has not found a match for any I, it returns no match. And if you ever reach the end of the pattern in the checks, then you have found a match, right? Then you return this position where the match started. Is the algorithm clear? That's as easy as it gets. It's just 2 for loops. Now, interestingly, this is essentially what Java does in the index of method. And there's a reason for that it isn't often as bad. For example, in this, let's maybe play this through quickly. So we would try to find this pattern ABBA in this text. So A matches and B matches and B matches, but then this is a mismatch. So it doesn't occur in the first position. So you try again here, but there's immediately a mismatch. So you don't even have to compare these other 3. Same here and here. Then we have to start comparing again. And here's a mismatch. But then we again immediately stop here, whereas here we have to continue longer. And indeed, this is a match. So we have found our match here. And here's the same thing in nicer. So red is a mismatch. If you compare how many comparisons in this concrete instance were needed, it's 15, whereas this worst case n times m is quite a bit more. So it's actually not that bad. Often, if the inputs are not adversarially chosen or you're very unlucky, the brute force method is not unreasonable to take as a start. But for a good library implementation, it maybe isn't robust enough. And the reason is this example. So I said the good thing already about it. It's easy and it's not always bad, but it can be quite bad. In this example, the text is quite boring, and also the pattern is fairly boring, but nobody stops your users from checking patterns, string matching with these inputs. And in this case, you need exactly all the comparisons that you could possibly need. Okay. So nice and easy, not always crappy, but not quite good enough for a robust implementation. We can learn something from this worst case example here. In particular, it seems like at least this worst case has a lot of self-similarity. The text is the same character repeated all over, and the pattern is not too far from that either. So maybe instead of treating this as a bad case, maybe we can take advantage of this fact. And also in some cases here, like you compared A's up to this point, and then okay, there was a mismatch, and it was kind of stupid to start again. But for these next 3 A's, these 2 A's you already checked, and you already know that the text has A's there. So if you were a bit smarter about looking about your pattern first, you would have been able to figure out that you don't have to compare those two. It's clear that they're implied matches. But of course, the brute force method wouldn't be able to figure this out. So what can we do to improve this? There's really 2 big approaches, and the second we'll look at in the next subsection. Both approaches essentially mean don't just start comparing and make uneducated guesses, but instead first spend a little bit of time on analyzing the situation. And that can either be the pattern or the text, depending on the situation. In this unit, we'll treat the situation as dynamic. The text can change all the time, and the pattern is given to us when we query for it, but we assume the pattern is small. So taking some time to analyze the pattern is justified. And so we'll have 4 different ways that take a look at the pattern and try to do something smarter with it than the brute force method. The other option is also interesting, though. If the text can be expected not to change all the time, then you can instead pre-process the text, and that can mean you might be able to find matches much faster. And we'll do that in Unit 6. You may have heard of inverted indices or even suffix tree suffix arrays. That's what we'll look at there. This is what's behind search engines, or at least the simpler versions of those. They're the textile websites. Now they do change once in a while, but not so often that you can't recompute this index. But for now, let's stay in the first approach, where the text can change all the time. We have no control. And instead, we're only looking at the pattern before we start matching. Okay, let's do this one and then a little break. Before I can already start this one. So this unit will use some terminology from automata theory of formal languages. It's not super important that you know these, but if you do, or if the majority of you did, I would maybe draw a few extra connections in that direction. If you all take A, then maybe this is not as useful. It seems like a lot of people take A. In the next subsection, we want to look at the first non-trivial algorithm to find string patterns in a text, and we'll use finite automata for this. Now, I asked you to tell me what you know about these topics, And it seems either many of you love emoji or you haven't had an automata course. So I'll keep the references to all this a bit short, but at least you will learn something in this lesson that's useful. And there's also substantial fraction of the people who've seen that before, but might have forgotten a bit of it. For those, it's a nice refresher then. So in essence, what this subsection is as you ask me a practical question, find this pattern in the text, and computer scientists or theoretical computer scientists tell you, well, this is something we know how to do. Listen, here's how to do it. Theoretical computer scientists talk about languages, formal languages, which are just sets of strings. And you can write formal languages, for example, like this. You can say this is the language of all strings that have something. Sigma star is an arbitrary string, arbitrary length. Then the pattern, and then another arbitrary string. And now you're asking if your text is part of this language. So you can formulate it in this string matching, in this deciding whether a string is part of a formal language. You can formulate the same question in this problem. Now, moreover, this language on the right, this sigma star p sigma star, is a regular language, in case you've heard this before. So in particular, you can describe it as a regular expression, which this kind of already is, depending on the notation you allow. And it also means whenever a language is regular, there exists a deterministic finite automaton to recognize it. So we can just simulate this automaton feeding the text through. And so in n steps, this tells you if the pattern occurs or not. That's really cool and pretty opaque if you haven't heard about all these concepts. So theoretician says job done, but programmer says hold on a sec. There's a few problems you glossed over. And the first one is not the serious one. You can fix that one. But the second one is a little more serious. We say in this step, there is some automaton, but that's not enough to program it. You have to find it. You have to explicitly construct it. And there is a way to do that, but it can produce automata that are exponential in the length of the pattern. That's kind of a problem. We don't want that. That's really expensive. Now, let's ignore those two problems for a moment and see why, despite these problems, the approach actually works. It's just not completely obvious, even from the theoretical perspective, without looking at it closer, why. But let's assume first, let's make a visit to wishful thinking land. Let's suppose we already have an automaton that solved this problem for us. How would that work? Or formulate it differently, if you've never seen automata, now is the time to wake up, because I'll tell you what they look like. And so here is one. This is a deterministic finite automaton, abbreviated as DFA. There are these little diagrams with states and arcs. They have a starting state, that's where the arrow points to, that comes from nowhere. And then they have a bunch of states, which are just these circles. And the automaton at every point in time is in one state. And as the arrow suggests, initially we start in 0. A second feature, the states can be like these, which are with just a single line. These are non-accepting. If you read the string left to right, if you read the string through and you stop in a state that is like this, then you reject the string. And if you stop in a state with the double line, you accept the string. Now, automata, what does it mean, accept and reject? They're devices to tell you if a string is part of a language or not. And remember, we'll use this on this language. So the automaton will tell you if the pattern occurs or not by accepting or rejecting the text. That's how this works. Now, what I haven't told you is how the automaton runs. and I think let's just do this on an example. This is actually quite intuitive. We start in state 0. That's shown in this table down here. And now I'm reading the first character of my text. And well, here it happens to be an A. Then I look at my state and check the outgoing arcs, and there must be exactly one with an A. In a deterministic finite automaton, there's always exactly one outgoing edge with a letter for each, well, there's one outgoing arc for each letter in the alphabet. Now, one violation is allowed. If there's no arc, then you go to an implicit garbage state that you can never leave, which means if there ever is no arc for your letter, you're immediately reject, because you're trapped in this doomed state. We don't draw those because sometimes automata have tons of arcs going to this garbage state, so that would clutter up the picture. But that's the only exception. What is never allowed is having two outgoing arcs with the same letter. All right. So from 0, there's an arc to 1, so we are in state 1 now. If we read another A, we follow this arc, so we're again in state 1. Now we read a B, that brings us to state 2. Now we're in state 2, we read an A. Where do we have to go? Straight. We follow this one. From the 3, a C brings us back to 0. From 0, an A is back to 1, and we stay in 1 with another A. 1 with a B brings us to 2. Then A brings us to 3. And now we go forward to 4. And actually 5, and 6, and 7. And here we stay with whatever letter, we just stay in 7. So the automaton has accepted the text, which means there was a pattern occurrence somewhere in the text. But this doesn't immediately tell us where the pattern occurred. But if you pay close attention, the first time you reach state 7 signals the end of the first occurrence. And after that, we just stay in 7 forever. So it's not very interesting. And so you can calculate back from this, you know how long the pattern is. So it must have been at this position, whatever that is in the text. You can keep track of the index in the text. Okay? That's how a deterministic finite automaton works. And this automaton magically does the job in that whenever I feed it with a text that contains this pattern, it will end up in the accepting state, because you basically march down to the right through the states. What's not obvious is if you take any of the other arcs, it will not mess things up. You will also find any occurrences that come later. But we'll come back to this. So here's that in nice again. So why does this automaton work? And how can we possibly construct this if it's not already given to us? The key insight is this in the box, and it might need a second to digest. So it expresses what a given state expresses in knowledge about the text. It means if we're currently in state Q, that means the text ends with a prefix of the pattern, namely up to the qth position, but excluding that one. And also there's no longer prefix of the pattern that we have seen up to this point. Okay? So the state number is the length of the longest prefix of the pattern that's a suffix of the text we've seen so far. Anyone followed? I hope this is somewhere written here in roughly the same way. Well, this is maybe the shorter way to express it. Now, why is this enough to determine if we find a pattern occurrence and how to do the next step? Because this is just saying we can somehow guarantee this invariant, that we always keep track of the longest prefix of the pattern that we've seen. But we don't know what the text looked like before this occurrence. So how can we keep track of this invariant? So if we find the next character and it matches, then we just make Q1 bigger. That's easy enough. That is why we have these edges to the right whenever we find the next character in the pattern. So for example, if we're in state 3, it means we have seen the first 3 characters of the pattern, which is ABA. We don't know what the text was before, but this is where we currently are. If the next character in the text now is a B, that happens also to be the 4th character in the pattern. So we just go to state 4, expressing the new knowledge that the prefix of P is now 1 longer. The interesting case is when the next character is not the right one, not the one that the pattern has. So like in this case, in state 3, the C, and here C is for an arbitrary character. What we know about the text is it ends with this prefix of P and this one new character. We also know that this is not a prefix of P because the C doesn't match. Okay. And the third thing we know is without this C, this was the longest match, the longest prefix of P that we could find. So in pictures, that's what the text looks like. In this situation, we have this prefix and the new character. Now what we try to find is a new state, which again is the longest prefix of the pattern. So we want to shift the pattern to the right so that now we again find a partial match. And the good thing about this is it only needs the portion of the text that we know. It is irrelevant what's to the left, because we only ever shift the pattern to the right. So we can, intuitively, we can just go through all the possible choices. We can shift the pattern by 1 and check if all the characters aligned match. If not, we shift 1 further, and so on and so forth. If we do this in our example, we have, so this was the case that, okay, let me leave this one. So we go to state 4. But then the other option was, if I have ABA and now I read a C, there's nothing in the first few characters of P with a C. So if I find a C in the text, I know there's no occurrence of P containing any of these positions. I have to shift the pattern entirely to the right. So the earliest occurrence can be starting after the C. And that's why I go back to state 0. The longest prefix of the pattern I can have seen at this point is empty. There's no way I can start with a C. Okay? So the important message is that this new longest prefix is always shorter than the previous one. So all the information we need is contained in what we know about the text so far. What we haven't figured out yet is how to efficiently find this, this next transition. And I think that's what we'll look at after the break. So let's continue in 5 minutes. 58.
Yeah, I have it. In the definite automata, can you please open the diagram? Like I have that also straight, like
Which diagram?
and then the one with the states. We were, yeah, that, yes. Okay. So here at 5, if we have like from 4 we got A and we got 5.
Yep.
And after we got another A, so
Let me go to the previous slide where it's bigger.
yeah, so it's go back to 1. So why doesn't it repeat itself on its loop on itself rather than going to 1?
Okay, so you're in 5 and you read a B and another B. Is that what you mean?
No, at 5 we read another A.
Okay, if you read an A at 5, you go to
Yeah.
1.
Why it is going back instead of looping on it itself?
Because there it was reached by an A, right? That's what you mean?
Yeah.
The reason is you have to look at the entire history that you learned so far. So in 5, you're in this state. It means you've seen currently the first 5 characters, which is A, B, A, B, A.
Yeah. So it is the pattern we are looking for, or the entire text we are looking for?
Well, we're looking for the pattern in the text.
Okay.
But the thing is, you don't know what the text is really like. You only know that it ended with these 5 letters.
Okay. Yeah.
And you want to find now, with this new A, we couldn't extend it to the 6 because, well, we would have expected a C. If now an A came, we have to find what's the longest part of the pattern that I can put below this here so that it still aligns with what I know about the text. And because there's no double A in the pattern ever, the best I can do is I can take this A as the first.
Yeah, okay, and try to go for
from there. And
initial stage.
that's why it goes back to state 1. Right?
Yeah. Thank you.
Yeah, it's a little subtle, right?
Last, no, I don't understand by the Q find that's
It's basically because of this third condition. Maybe the easiest is suppose it was the same as Q or even longer. Okay. If it was longer than the old Q, you could delete the last character from this match, and then it would have already been in match before, one step before. But Q was by assumption the longest prefix that we could match with the text at this point. So that's not possible.
So, what means prefix?
Well, it's just a substring that starts at the beginning.
Like this.
Yeah.
So this part is prefix.
That's a prefix of the pattern.
Thank you.
Today, live, I have to finish this.
Thank you.
No, I can't. So, finish this. I always get 15 now. I'm going to put in a signature. Until yeah, and I don't
All right, guys, time to move on. Some energy left. All right. In the next subsection, we want to look at how to construct these automata that we've just used. I've explained to you briefly, if you're given such an automaton, how you can use it to search the text. And I'm motivated slightly a bit why this automaton contains enough information to do this task. But it's maybe not quite clear how to efficiently construct this automaton. So let's have a look at this. If you have this formal language background, you might think, why don't we use a simpler automaton, the non-deterministic finite automaton, instead of this deterministic one? The reason is that the non-deterministic automaton is really easy to write down. It is simply writing down the pattern like this as states and pretty much no other transitions. How does a non-deterministic automaton work? The non-determinism part is now that you have the option to have two arcs with the same character. And in particular here, you always have to decide, do you follow this track now or do you stay with the current A in 0? And the automaton doesn't help you. It just says, you figure out the way to decide where to go. And it accepts the string if there is any way to get to the accepting state. But if you took the wrong turn because you decided, oh, I'll stay and wait for another round, or you went running down this track and got trapped, that's your problem. You have to try to find any possible sequence through the states. And another way to say this is that at any point in time, you have to think of being in a set of states as opposed to a single state. So let's see how we can make sense of this, because it's a nice precursor to what the construction of the deterministic automaton does. So in principle, we could use this automaton. So again, this automaton is really easy to construct. You just write the pattern down, put states and one arc, and you add these transitions here where you can stay with every character in the 0 state. It's trivial to construct, and you can use it for string matching. Just there's a catch. But let's first see how in principle we can do it. And the key insight is you can at any point in time remember to be in a set of states as opposed to a single state. And whenever there's a way you reach the final state, so whenever there's a final state in your current set of states, you accept. It's a little bit like quantum computing from the spirit, but it's different in many ways. So you shouldn't mix up quantum computing and non-determinism, but it kind of has a similar flavor that there's parallel universes where you could have done different things. But that's where the analogy stops a bit. Let's do it on an example again, so same example as before, just to see how this works. We initially start in only the start state 0. So far, so good. Now, if an A comes, I can go to state 1, but I could have also stayed, so I just do both. And after that, I'm simultaneously in state 0 or 1, where I could be in any of those two states. If I do another step A, it doesn't really bring me further from 1, so this branch that was in state 1 goes into the garbage state and dies out. But I've also been in state 0 in this point, so taking another step A brings me again to state 1 and back to state 0 at the same time. So after reading another A, I'm still in this state set 0, 1. If I now read a B, things get slightly more interesting. I can stay in state 0, but for the parallel universe where I was in state 1, I now move on to state B, state 2. And from there on, we get another branch. So if I'm in 0, 2 and I read an A, from state 2 I can go to state 3, that's great. From state 0 with an A, I branch into 1 and 0. So I'm now in 3 states, 0, 1, and 3. If I read a C at this point, these two die out. From 3, I cannot go anywhere, so end of the line. From 1, I die out, go to the garbage state. So the only thing that survives is state 0, which always survives because I can always stay there. So after this transition with C, I'm back to knowing nothing in a way. And then things repeat indeed. So I have A and A again. You will recognize the same as before. Then B, same as before. A, same as before. But now the next character is different. We're in the part of a match. So now if I read a B here, I have to go through all 3 states and see what a B does to them. From 3, I go to 4. From 1, I go to 2. And from 0, I can only stay in 0. So it brings me to the states 0, 2, and 4 after reading the B. If I read another A there, I'm now branching out into 4 different universes. All of these, so 4 goes to 5, 2 goes to 3, and 0 goes to 1 and 0. So now in these 4 states. If I read a C now, 5 survives to 6, the other 2 die out, and 0 remains. But I'm still in states 0 and 6. And reading one more A brings me from 6 to 7. And that's all I need to know. The other states are interesting to know of. But as soon as you've reached the accepting state from any of these branches, you accept the string. Okay? Now it's a nice exercise to compare this table to the one before, but I'll leave that for you at home. So again, we can not only do this in this example, but in principle, whenever you have a non-deterministic automaton, you can construct the deterministic from it. You can even minimize the DFA afterwards if you feel like it. But this problem 2 from before kind of remains. The algorithm to compute a DFA from an NFA in general has a blow up where if you haven't seen this, think about this. You get a deterministic automaton by just taking the set of all the states in the deterministic automaton are all subsets of states in the non-deterministic one. And then you're doing exactly this simulation. You go from one set of states to another set of states. That's deterministic. The problem is there's many sets of states, so we're still not completely happy. But these 3 people, in essentially 2 independent ways, discovered that our string matching automaton is not a generic NFA. And indeed, if you apply this construction here, it doesn't actually lead to this exponential blowup, or you can at least sneakily avoid it. And you can construct the DFA by adding one state at a time and avoid this blowup. And so what you construct is first an automaton for the pattern up to the first j characters. And then you add the jth character at the end and see what that does to the automaton. So this previous automaton, sorry, for j minus 1, it will have states 0, 1 up to j minus 1. It will have this general shape, and it will have various arcs going back. And so if we want to go now to AJ, the automaton for the pattern with one more character at the end, what we'll always have to add is the new state j. And that just gets the transition pj. And we also need the failure arcs. So what happens if I am, so remember here in the previous automaton, these were not really there. Instead, they were loops on the accepting state. Sorry, I have to make the picture a little bigger. This is always a mess with the indices. So we have j minus 1, but we also have state j, which is one after reading the previous character brought us here. So this one has a failure link somewhere back there, but this one didn't. Now what I add to the new is state j plus 1, which is reached by the jth character. And I have to find out where do these go back. So instead of staying there, I now have to find where does this branch back to if I'm reading a character that's not the right one in the pattern. Okay, so I need a new state. This transition is easy, but I also need the other transitions, and these are the tough ones to figure out. And remember what it meant to be in a certain state. It meant we've seen a certain prefix, and that was the longest that we know that we could have seen up to this point. So let's go through this. So delta is the target of this arc. Delta jz means I'm in state j, and I'm reading a character c. And now I have to jump back. So these are only for the arcs that don't bring us forward. And that leads to a state delta jc. That's the target of this arc. And we want to know where this is. Now, remembering the invariant, it is the state, so it's the length of the longest prefix of this text, of this thing, that we can find, so that it's always also a suffix of this. So I think this is best shown in a little picture on the side. So we know that text currently looks like this. We have P0 up to J, but excluding J. And we read one more character C, and it's not the right that we would have expected here. And now we're trying to shift the pattern forward by as little as possible, so that I here have the same, but with the first character omitted, and again the character C at the end. And I want to shift this forward so that these characters all match. Okay, that's the goal. Now the insight here is, so the insight really is into this, in this equality. How much do I shift this forward? That is something that the smaller automaton can tell me. Because this never uses the last character of the pattern. It only uses up to the jth position. So I can use the automaton I already know and simulate that automaton to tell me what should be the state where I'm supposed to be at now. So you can simulate the old automaton, aj-1, on this text. Just suppose you start reading the text again, but you omit the first character of the pattern. And so we'll see how this works in a second. Taken as this, so this would work. You can construct the automaton like this. But it seems each time you compute one more arc, you have to simulate the automaton. So you have m states in total, you have sigma arcs per state, and each time you would have to simulate the automaton one smaller with something on the pattern, so that would take another m time. And so this seems a bit expensive. And there's another little trick. The second insight from this algorithm is that we don't have to run this automaton from scratch. Because if you did this simulation it would always start with the same prefix, P1 up to J. And only the last character differs. We have different characters C, so we need a different arc here for the different characters in the alphabet that are not the correct one. But the simulation would always use the same prefix. So we don't really need to do it. We instead can just remember what is the second to last state and go one step from there. And so that's what we can do. We maintain a state X, which is the state where we would have gone with this, reading this in the automaton. And from this state, we go one further arc with all the different characters. And then we put these into the delta table. There's a nice graphical way to show this, and it's nicely shown in this video. So I just show you this instead of trying to recreate slides for it. I hope the sound is audible.
Let's take a look at the demo because the full construction for the VFA. Here goes, again, I want to say very careful what I said. Match transitions are easy, how we build those, and we're going to start at position 0, and mismatch transitions are easy. So now when we move over, X is, we're at position 1 of the pattern, X is where we would be if we started out without that character, which is the empty string. So we start out with 6.0, first to 0, and we can do that without any further reason. And now we've got X initialized. So now what we need to do is fill in the mismatch transitions for state 1. So what are they? They're what would happen if we found those characters and we were in state X. If we found an A, we go to state 1. If we found a C, we go to state 0. When you notice, that's just taking the entries corresponding to the entries we need from X's column and putting it in J's column. That's all it is. Then we need to update X, which is where it would be if it has to be. So we'll say X will stay in state 0. So now let's look at state 2. So we need to fill in what would happen if we got a B and what would happen if we got a C. Well, what would happen if we were in state X and we got a B or a C? So all we do is move those two zeros over to column 2. And then don't forget, we have to update X, and the X goes where the machine would go to column A. That's the difference between 2 and 3. So we just move X to state 1. So now we have X in state 1, and we're doing position 3. And now you can see how really simple the algorithm is once it's filled. So now the mismatch transitions are A and C, and that's what we have to fill in for column 3. But those mismatch transitions we already computed. That's where X would go. That's where it would go if we happen to be in state 1. So we move the 1 and 0 from column 1 over to column 3. And again, we update X. And we'll see a B, X goes to state 2. And again, we can check what is X supposed to be. It's supposed to be where you would be if you started the machine on the pattern of the first letter cut off. So it's supposed to be where you wind up if you got B-A-B, B-A-B. All right, now it's straightforward. State 4, we have to fill in B and C. We go to X's column and copy the B and C from X's column. When we update X, that's position A, and go to state 2. Now we're ready for state 5, which is actually completed. And we need to do A and B, and we get those from X. If it's an A, it's a 1, and if it's a B, it's a 4. It's just going to come over. And then when we do the C, we get the accept, that's the, we would do update X, get it ready. when we get to state 6, we're done. And again, if this is a double check, X is where you be, if it's going to be A, C, A, C. That's the construction of this Knuthmore stack, DFA.
All right, the audio wasn't great, but I can try to smuggle in the original video into the recording if you want to watch it again. I think, I know it's maybe a bit slow, but the construction is very nicely shown, that it's very simple. If you look at this matrix of the transitions, you just have to copy columns. And so executing it by hand is maybe the better way to understand what's happening here. Let me wrap up this subsection by looking at how well these methods work. So this might not have been obvious from how I showed this on the examples, but if you've given this automaton, finding the pattern in the text is really feeding the text through the automaton. And this takes n steps because it's a deterministic automaton. So in each step, you just need to find what is the transition I have to take. That brings you to some other state, and then you keep going from there. You can do this with table lookups for this delta table that you've seen in the video. Building the DFA necessarily needs as much time as you need arcs to fill. And there's m states, sigma arcs per state. So that's the number of arcs, sigma times m. And with the construction from the video, it actually is constant time per edge. So in total, if you sum this up, we spend m times sigma time on the pre-processing stage, plus n for the matching, so that's the total time. That's already much better than n times m if m is not super small. And even if m is fairly small, the pre-processing step is also fast, right? The space is what you need for this transition table of the automaton. So again, you need one entry for each arc. M times sigma is the number of arcs. So that's roughly the space you need for executing this algorithm. In terms of the time, this is actually really hard to beat for the matching part. And because you do one table lookup for each character in the text. And at least if the alphabet is small, this is also the best possible total time. The big downside is the space overhead. And think again, so sigma is the size of the alphabet, which can be small if you have something like DNA, but it could be the Unicode alphabet, which is 150,000 characters. So you're trying to find a little string like love in all the works of Shakespeare, and you spend, I don't know, a megabyte of space for building this lookup table, and you have to fill this first. So you're probably halfway done if you just use the brute force method. So this doesn't sound too scary using 1 megabyte of memory, but remember it grows with the pattern length. And it's just a very, very basic task that you might use many times. So you want something really efficient there. So we'll try to work on this a bit more. Especially bring the space down. And that's what then is called the Knuthmore spread algorithm. I think we'll reserve this gem for next time, where we have fresh energy. It'll bring all these ideas together and just take this idea of the automaton one step further to get rid of this dependency on sigma. All right, all for today. See you on Thursday. Remember the videos. If you have not found an article yet, do that as a matter of urgency.